Hi, I'm going to go through a video on combinatorics and probability. Combinatorics refers to different counting methods. And I'm going to go through three different counting methods here: the multiplication principle, permutations, and combinations. I'm going to go through 10 sort of basic examples. This video is made for the Math 106 class, and these are the types of homework questions that I typically put in that I typically use in that class. Okay, so the first example says, to unlock an iPhone, a user must enter the correct 4-digit PIN code. How many 4-digit PIN codes are possible? And if you get 10 attempts, what's the probability of randomly guessing the correct PIN code in 10 attempts? Alright, well, this first example starts off demonstrating the multiplication principle. Multiplication principle is also sometimes called the fundamental counting principle or just the counting principle, so you might see it referred to as those in other places or even in my notes. It's the one where I will typically start off by just putting little dashes that represent decisions that have to be made. I think of a sequence of decisions. In this case, I'm thinking 4 decisions. And each decision I have to think, how many choices do I have? And if you're talking about a 4-digit PIN code, digits are the numbers 0 through 9. And so if you count 1 through 9, of course that's 9 possibilities. The 0 makes 10 possibilities. So what I'm thinking is, in each of these decisions I have 10 choices. And the multiplication principle says that you could actually calculate the total number of possibilities by just multiplying the number of choices you have in each decision all together. In this case, we get 10,000. Sort of begin to imagine it as like a tree that's starting to grow. With the first decision, there were 10 branches in that first decision, and each of those 10 branches would then have 10 more branches, and that would be followed by another 10 branches and another 10. And so ultimately at the end you have 10,000 different branches that you could have followed there in selecting one digit at a time. So how many 4-digit PIN codes are possible? The answer is 10,000. Now the other question says that if I have 10 attempts, what's the chance that I can get it right? I would look at that as a fraction to begin with, and I would think about the total number of possible 4-digit PIN codes, which we've just calculated is 10,000. I begin with that number on the bottom so I can sort of think about the big picture. How many total possibilities are there? Now if I went through 10 different attempts, it wouldn't make sense to try the same thing again, of course. So you could naturally assume you'll take 10 different PIN codes and try them. And so each one of those you have a 1 in 10,000 chance of it being correct, and so it could be either the first or the second or the third or the fourth or up to the 10th. So there's really 10 different possibilities you're trying out of 10,000. So you have 10 ways of getting it right out of 10,000, and so you could reduce this to 1 in 1,000. So I have a 1 in 1,000 probability. If you just picked up that phone and tried before it locked you out and erased the phone, you have a probability 1 over 1,000 of getting it right. Okay, let's go to the next question. Number 2, a password consists of 8 characters. Assuming any upper or lowercase letter and any digit 0 through 9 can be used, how many passwords are possible? So again, it's my multiplication principle. And here I've got 8 characters, and so I'm going to start off with the same idea of these little dashes. These dashes are the decisions. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8 decisions, because each decision is which character or which digit to use in each of the positions of the password, each of the characters of the password. And of course we're talking passwords here, so of course you can repeat a letter. You can intermix the letters and numbers in any particular order. And so you think about 26 letters when you say A through Z, but times 2, so we're counting 26 letters in the alphabet times 2 because there's upper and lower case. So 26 times 2, that's 52 actual letter characters. 52 letters plus 10 digits makes 62 characters total. So I have 62 possibilities in each one of these decisions. 62 possibilities for what the first character would be, 62 for the second, and so on. I would write this as 62 to the power 8 and use a calculator. On the calculator, this is such a big number that it writes it in scientific notation. I'm going to round off and say about 2.18 times 10 to the 14. Now, unless it says in the homework that you're working on to write otherwise, this is fine to write it this way. It's convenient to write big numbers in scientific notation, but it's also just kind of interesting to observe that we could move the decimal over 2 places and make this 218 times 10 to the 12. And the reason I'm doing that is because I know a word for 10 to the 12. It's trillion. So this is roughly 218 trillion, and it's just fun to recognize big numbers like that. I'll just mention 10 to the 6 is a million, 10 to the 9 is a billion, 10 to the 12. Notice how I'm going up by threes. That is, every time you multiply it by 1,000, there's a new name for the number. So you could say that a billion is 1,000 million, and you could say that a trillion is 1,000 billion, and one more just to have fun with this. 10 to the 15, that's a quadrillion. The Math 106 class, I'm not expecting any of you to memorize any of these or anything like that. This answer was fine here, but I just thought this was kind of fun. You might think this is kind of interesting. Just these names are fun to say. Another 3 more zeros, and I'm at 10 to the 18. That's quintillion. One more. Sextillion. 10 to the 21 is a sextillion. All right, let's move on to number 3. A multiple choice test consists of 10 questions, and each question has 5 choices, A through E. How many ways are there to complete the test, assuming every question is answered? Okay, you could still go to the fundamental counting principle, or the multiplication principle as it's known, and think about this as a sequence of decisions. In each decision, how many choices do I have? I've got a sequence of 10 decisions. Question number 1, what am I going to write? A through E. And number 2 and 3 and so on. In each one of these, there are actually 5 choices. And I'm multiplying all these together. So that means I have 5 to the 10th power. 5 to the 10th power is a really big number. We'll have to use a calculator. 9, 7, 6. We get 9, 7, 6, 5, 6, 2, 5. So almost 10 million different ways to go through and just randomly guess at the answers. So almost 1 in 10 million chance of getting it exactly right on just a completely random. If you didn't know the questions and you were just completely randomly guessing, and if they were really randomly selected what the right answers were, you'd have about a 1 in 9,765,625 probability of getting it right all the way through on every one of them. Very unlikely, right? That's odds that are similar to winning a lottery. Next question. Number 4 says the Kentucky Derby is run with a field of 10 horses. How many ways are there to select the first 3 finishers in the correct order, and what's the probability of selecting the first 3 finishers of the race in the correct order? We'll start with the first question. Just how many ways? That's the counting question. That's the combinatorics question, and I'm going to use permutations here. This will be the first example where I can really refer to it as a permutation. Permutations refer to the number of ways of rearranging some selected items, and if we'll start with the assumption that they're all different items, so that each arrangement is different. Right? So we have 10 horses, and we're talking about rearranging the first 3 that finish. Each of those could be a different outcome. So how many ways are there to select the first 3 finishers? Well, ultimately, really, this is actually still the fundamental counting principle. In fact, I would say that the permutations and the formula and the shortcuts that we use for permutations are really just a special case of the fundamental counting principle. So we could do it that way still, and that's how I'll start. I'll explain it first as there's a decision as to what horse comes in first, as a decision about what horse comes in second and which one comes in third, and how many sort of choices are there in which one comes in first. Or there's a decision you have to make when you pick, if you are picking, who do you want first? You'd have 10 choices there because there are 10 horses. And who would you put second? We don't know what anybody would necessarily pick as their first choice, but once you've picked the first choice, there's only 9 remaining choices. So there'd be 9 possibilities for your number of choices for your second decision, and there would be 8 choices for that third position because you already had 2 horses chosen for the first and second place. When you multiply these together, that's 72 times 10. That's 720. That answers the first question, how many ways? Now the second question, what's the probability of selecting the first 3? Again, I can start with the total number of possibilities. There's 720 different ways that 3 horses from the 10 total could be rearranged in the first 3 spots. And out of all those 720 different ways, one of them would be an individual choice that somebody could pick, and so you've got one shot out of all those 720 different things that could happen if you were betting on such an event to pick the right 3 horses in the correct order. It's what's called the trifecta, the probability of winning a trifecta when there are 10 horses. Picking the top 3 that finish, the first 3 that finish in the correct order, that's a 1 in 720 probability. Now, I should probably go back to the counting question. So this is the answer to the probability question. But I should go back to the counting question for a minute and talk about a sort of shortcut that we have, because that calculation happens often in many of the examples that will follow. It's a sort of standard kind of counting question. What I could do here is say, to count the number of ways of selecting the top 3 horses in a particular order, this is a permutation question that we could write 10p3. You could say 10 permute 3. What this represents, this is the total number of items. Here the items are horses, and this is the number selected. And they have to be different. They have to be different items. And there's a formula that we could use for this calculation that is 10 factorial over 10 minus 3 factorial. 10 factorial means you're multiplying 10 times 9 times 8 all the way down to 1. This is 7 factorial, so we have... Now you notice how if I was doing this by hand, I could actually just say cancel the 7 factorial on the bottom with the 7 factorial that you have right here. All this would cancel out, and what I'm left with is just 10 times 9 times 8, which is the calculation that I'd already done, 720. In fact, there's another sort of shortcut that I sometimes use, and that would be if I wanted to do 10p3, sometimes even without picking up the calculator, I could do the calculation where I say start with the number 10 and multiply 3 numbers counting down from 10. So that would be 10, 9, 8, because that's 1, 2, 3 numbers counting down starting at 10, and I get the answer that way. So that's a useful little shortcut that we could use, and you could find this on any scientific calculator. Look for a probability table. Maybe some calculators you'll have to hit the, on the 84s you hit math, look for probability. On the TI-36s, look for the PRB button, and then scroll over to find this. And you could Google and YouTube on how to use different calculators to do these calculations. Okay, let's look at number 5. Suppose there are 6 movies playing at the local theater. How many ways are there to rank those 6 movies in order of best to worst? So I could go back to the fundamental counting principle, multiplication principle, and do it again that way. Every permutation problem I could actually do with that starting principle. It's just that the permutation is a kind of a shortcut for special situations where the numbers are counting down. And so that would be happening here if you were ranking the movies. It's specifically the fact that it mentions ranking. So when you see these words like arrange, rank, order, you know that you're looking at permutations. So in this case, if we've got 6 movies, we could start off it with the original multiplication principle and say that there are 6 decisions. 1, 2, 3, 4, 5, 6. So how many choices do you have for your favorite, the best movie? There would be 6 choices. And how many choices do you have for the next decision? The next decision being, what's the second best movie? There'd be 5 choices. And then 4 after you'd pick 2, 3, 2, and 1. When you multiply all that together, that's such a common situation to have to calculate that we have a special symbol for that. That's what we call the 6 factorial. And 6 factorial, well, that turned out to be 720 also by just pure coincidence. So that's the answer for that one. Note that if you wanted to use the permutation formula, you could, and it would give you the same answer. It's just that I would do 6 items, choose 6, and rearrange them. And 6 permute 6, well, that's going to be 6 factorial on top divided by 6 minus 6 factorial. And that means I got 6 factorial on top over 0 factorial. And what we do here is we say 0 factorial is defined as 1. And the reason for that is that it just makes formulas like these permutations and combinations formulas work in including the case where these two numbers are the same. Because if they're the same, you get a 0. We'll just say that 6 minus 6 is, of course, 0. And we'll just say 0 factorial is 1. So you have 6 factorial divided by 1. 6 factorial, that's 720. Alright, now on to number 6. A jury pool of 20 people are called to a courthouse. How many ways are there to select 12 to serve as a jury? Well, this will be the first example where I can describe it as a combination. I'm still ultimately really using the fundamental multiplication principle, but I kind of use a shortcut for this special kind of scenario. I've got 20 people, so you could say 20 different items in general. When I have distinct different items and I'm selecting from that group and I'm not rearranging them, because you're just talking about 12 people for the jury. In this particular question, there's nothing that refers to arranging, ranking, ordering those items that we're selecting. So this is where I use a combination, and to get right to the shortcut, it's going to be 20 C 12. You could read that as 20 choose 12. And the formula that I use for this is 20 factorial on top divided by 20 minus 12 factorial, but then 12 factorial. So I start with the total number of items, put that on top factorial. Then I subtract these two numbers, put that on the bottom factorial, and then finally also on the bottom you need this number factorial, right? This represents, well, let me do one step of simplifying here. This is 20 factorial on top over 20 minus 12, that's 8 factorial, and you've got to do these parentheses first, of course. 8 factorial times 12 factorial. Now what does this represent? This is the total number of items, and to use this formula they have to be specifically different items. This is the number selected. And this combination formula is when you're selecting items from a larger group and you're not counting the ways in which you could rearrange those items. You could look at this as if you actually wrote this all out. Now there's a button on the calculator and you really should use that button. It saves a lot of time. But let me write it all out just for the benefit of explanation. 20 factorial. Well, that'll take a second. So there we have 20 factorial on top. And on the bottom I have 8 factorial. All those multiplied together. And that's multiplied by 12 factorial. Now, if we're strictly looking for the fastest way to get this answer, just grab the calculator and type this into a calculator, 20 choose 12. Look for a PRB menu. Either you hit math and then go to PRB, or you actually have a PRB button right there on the calculator. But just for the purpose of explaining what it's actually doing, I'm writing it out in steps here to explain. Now, if I've got 20 factorial on top and 8 factorial and 12 factorial, the smartest thing to do here in terms of getting this quickly to the answer would be to cancel the 12 factorial from the bottom with the top. But rather than doing that, for the purpose of explaining, what I really want to do is actually cancel this first. I want to cancel these guys, 8 factorial with the 8 factorial that I have here. The reason I'm doing that is because I could explain this as 20 possibilities for the first person times 19 possibilities for the second and 18 possibilities for the third person because you'd already picked 2, etc., multiplying all the way down. And how many do I have here? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's for 12 people. So that would be the number of ways of picking 12 people from the 20, and that would actually count all the different rearrangements. So you notice that I'm actually also dividing this by 12 factorial. That would be the total number of ways of rearranging 12 items. And so this actually calculates the number of ways of selecting 12 people from 20, but divides out all the different ways in which they are rearranged. Now, I'm not even going to type this all into the calculator. I'm just going to go back and type this into the calculator. I know it's all going to come out the same answer. I just did this just to sort of try to explain where it comes from. If you type in 20, choose 12, so about 125,000 different ways to pick 12 people from the 20 that were available. Now let's look at question 7. Now question 7 says a jury pool of 20 people are called to a courthouse. How many ways are there to select 11 to serve on the jury and then 1 additional person to serve as the jury foreman? This question is different than number 6. Number 6, I just picked 12 people in any particular order and it didn't matter what order they were selected. But here I want each different possible outcome is counted where each different one of those 12 people could be the jury foreman. In other words, it would be a different result. I'm counting it differently if the first person was the jury foreman or the second or the third. So each of those is a different possibility here because it counts as different when one of them is a jury foreman and you're saying you've got 11 regular jury members and 1 foreman. That's making it different. Alright, so to figure this one out, you just say you've got 20 people and you're choosing 11, but of all those possibilities, now I want to multiply that by the number of ways of picking that one person to be a jury foreman from the remaining people. That means I'll take 20 minus 11, that's 9. So from the 9 people I want to choose 1. This 9 choose 1 is just a 9. So when we do 20 choose 11, we get 20 choose 11 is 167,960. Those are all the ways that you could pick 11 people from the 20. And then for every one of those possible ways of picking 11 people, you could then pick on 1 more person from the 9 remaining people, and that could be done 9 different ways. So we're multiplying by 9 here. I multiply these 2 numbers together, and I get, now I'm at over 1 million possibilities. 1,511,640 different ways. And that's the answer for this one. This one is so much more than the answer in question 6 because we're really putting some order in there now, but not ordering all the people on the jury. We're just counting it as a different outcome when each one of those 12 people could be a jury foreman or not. And so that multiplies the number of possibilities, counting the order in which that one person in that group of 12 turned out to be the jury foreman. I'll comment also that we're really mixing together 2 counting techniques. The first obvious thing that we're using is the combination principle. But I'm also using on top of that a multiplication principle because I'm multiplying these 2 values together. I'm multiplying the 167,000 ways of picking 11 people from the 20, and from every one of those 167,000 different ways, each one of those I could go 9 different ways when I pick that last person, that 12th person, to be the foreman. So that's the multiplication principle in multiplying these two numbers together. Okay, that's the answer to number 7. Let's move on. Number 8, suppose a committee consists of 10 Democrats and 5 Republicans. How many ways are there to select a subcommittee that consists of 3 Democrats and 3 Republicans? Well, this one works in much the same way as that last example. We can start to notice a pattern in each of these examples. You see, I've got 10 Democrats and I'm choosing 3, and there's no particular order in which those 3 are arranged. So we have 10 choose 3 as the number of ways of selecting 3 Democrats from the 10 available. And of all those ways that we could pick 3, we're going to multiply by the number of ways of picking Republicans. We have 5 Republicans. I want to choose 3 from among the 5 available. So I'm multiplying these two numbers together. 10 choose 3 first. Let's get that. 10 choose 3 is 120. And 5 choose 3. 5 choose 3 is 10. Now each of these you could possibly get without even picking up the calculator. 10 choose 3 is a little trickier. What's happening there is I'm going to start with 10, multiply 3 numbers counting down, but then divide by 3 factorial because I don't want to count the arrangements. So you've got 720 divided by 6, and that's the 120. That's where I get that number. 5 choose 3, you could say I'm also going to start counting at 5, 5, 4, 3, multiplying 3 numbers down, and then divide by 3 factorial, which is 3 times 2 times 1. This is 60 over 6, and that gives you 10. Some people do this in their head. Sometimes you do this often enough, it might be something that you could, when the numbers are small enough, you might be able to do that in your head. Sometimes it's faster than using the calculator. So that is 5 choose 3. There are 10 ways, if you had 5 items, to pick 3 of them, not counting the order. So 120 times 10, that's 1,200. Okay, now on to number 9. A lottery consists of selecting 6 numbers from the numbers 1 through 53. What's the probability of correctly selecting the winning 6 numbers? Now it didn't say, but I do mean with only one ticket. With buying one ticket, what's the chance that you match all 6 of the winning numbers and win the jackpot? Well, this is a probability question, so you want to really pay attention carefully as to whether it's saying, like the last one, how many ways, and when it asks how many ways, it's typically a big number, right? And then when it says what's the probability, it's going to be a fraction. So how many total possibilities do we have here? When you play the lottery, it doesn't matter what order you pick the numbers, it doesn't matter what order the numbers come up on the screen. If you have the right numbers, you would win. So we're going to look at the total number of ways of picking 6 numbers from the 53 available. And that's our number on the bottom. I like to start there because it's sort of like looking at the big picture. 53 numbers, pick any 6, doesn't matter what order. That's the total number of possibilities. Now if there's 6 winning numbers, how many ways can you get 6 winning numbers and none of the losing numbers? The other 47. If you take 53 and you minus 6, you'll have 47 numbers that you don't want, 6 that you do want. So I'll very much exactly really the same principle that I followed up here. I'll say of the 6 winning numbers, I want to pick 6. And of the 47 losing numbers, I want to choose 0. Now 6 choose 6, you really don't need a calculator for that one. 6 choose 6. If you have 6 items, how many ways can you pick 6 items? That's going to come out to be 1. And if you have 47 items, how many ways can you choose 0? That, logically speaking, you could say is got to be 1, because how many ways are there to pick none? One way, you pick none. You could also type it in the calculator. You could use the formula. Using this definition that we had previously established, 0 factorial is 1, you're going to end up with 1 if you use the calculator, if you use a formula, or if you just think about it. Anytime you do a choose 0, it's always going to be a 1. If you type in 53 choose 6, now I definitely don't want to do that by hand. That's a big calculation. That number comes out to be 22,957,480. So the probability is 1 out of 22,957,480. Imagine 22 million, almost 23 million different possibilities. You have to pick the right one out of those 22,957,480. different options. Picking the right one is the challenge of winning a lottery in a game such as this. There's the answer for that one. Also, just to sort of measure how really small that is, if we put that in decimal, it's going to probably come out in scientific notation on your calculator as 4.3558 times 10 to the negative 8. So because it's times 10 to the negative 8, I'm going to put 7 zeros and then a 4, let's say. So this is approximately 0.00000004. That's so incredibly small. It's basically 0. It's not exactly 0, but it's really, really close to 0 probability. Alright, let's take a look at the last example. Number 10. A lottery consists of selecting 6 numbers from the numbers 1 through 53, as in the previous example. What's the probability of getting exactly 4 winning numbers correct with 1 ticket? Well, if you get 4 numbers right, then you got 2 numbers wrong, and if you get 4 numbers right, you can still win some prize. Let's figure out that probability. So what I mean here with this event is match 4 numbers exactly 4 numbers. In other words, if you got 5 numbers right, you are also matching 4, but I don't mean that. I mean exactly 4 numbers right and exactly 2 numbers wrong. What's the probability of exactly that event? Start off with a fraction. It's a probability question. The total number of possibilities. If you've got 53 numbers and you're choosing 6, that's where you could begin with the total number of possibilities. Now, the pattern that's really useful here is to notice that there were 6 winning numbers, and you want to choose 4 and get 4 of them right. Actually, we're trying to figure out how many ways could you pick 4 correct numbers from the 6 winning numbers. But then multiply that by how many other numbers, what's the other category you could say? The other category is the losing numbers. How many are there of those? There are 47. That's because 53 total minus the 6 winning numbers leaves me 47 losing numbers, you could say. And of those losing numbers, I want to know how many ways could you pick 2. Now look at the pattern here. I have 6 and 47 together make 53. 53 was the total, which breaks up into these 2 categories, 6 winning numbers and 47 losing numbers. Of the 6 winning, I want to pick 4. And of the 47 losing, I want to pick 2. Also notice how the 4 and the 2, the numbers on top that I'm choosing, add up to the 6 that I have there. So the ones that I'm selecting break up into 4 from the category of winning numbers and 2 from the category of losing numbers. Alright, let's put each of these into a calculator and figure out what we get. 6 choose 4. 6 choose 4 is 15, and 47 choose 2. 47 choose 2 is 1081, and this number is the same as it was in the last example. So let's multiply these two together on top. 16,215 divided by 229,57480. Yeah, this ends with a 5, that ends with a 0. Actually, it could reduce, but in a situation like that, with these really big numbers, reducing it doesn't really make it that much simpler or more easy to interpret. It's certainly a situation like this, putting in decimal is much more reasonable. So if I type that, divide 16,215 divided by 22,957,480, you get about 7.06 times 10 to the negative 4 in scientific notation. And you could leave the answer in scientific notation, that's fine. But just because it's a lottery, somehow it seems kind of interesting to put it in standard notation to sort of interpret really how close this is to 0. The negative 4 means I'm going to move the decimal 4 places to the left. So that means I just want to tack on 3 zeros and then a 706. So this is a little more than 7/10,000ths as far as the fractional probability. And as a percentage, we could write that as a percentage also. Right, as a percentage, I'll move the decimal over 2 places. 706%. So almost a tenth of a percent, 7/100ths of a percent is the probability of getting 4 numbers right. 7/100ths, roughly 7/100ths of a percent, almost a tenth of a percent. All right, there's the end of example 10, and I'm going to stop this video here. I will do some more examples with probability in another video. I hope this was helpful, and thank you for watching.